Okay. So next topic, real analysis from chapter 1. So for chapter 1 of real analysis, we need to understand this basic concept, bounded and unbounded set, supremum and infimum. I need to recall two of the basic properties, that what we mean by finite and infinite set, countable and uncountable set. Basic understanding is needed, and then when I will cover the nested interval property and this representation of real numbers, then again I will come in detail and we will do several proof based on the concept of countable and uncountable set. And then after covering Archimedean property in detail, we will do the denseness property of rational number in R. So let us start it from the book of Walter Rudin, using the concept of function. This is the book Walter Rudin by Walter Rudin. I have taken this PDF. Sorry. I have taken this from Principle of Mathematical Analysis by Walter Rudin. Walter Rudin. Principle of Mathematical Analysis. Okay, so we will do this using the function concept, that how to differentiate between finite and infinite set, how to differentiate between countable and uncountable set, what we mean by at most countable. So let us quickly recall the function of the definition of function from your one can revise it from any book of 11th 12th class. We know that for given any two sets A and B whose elements may be any objects whatsoever, and suppose that with each element x of A there is associated in some manner an element of B which we denote by f of x, then f is said to be function from A to B or a mapping of A into B. The set A is called domain of f and the element of fx are called the values of f. The set of all values of f is called the range of f. So let me quickly recall this one through some examples, that see, this one is allowed for function every element. Let us note it as set A, set B. For non-trivial discussion, let us take A and B to be non-empty set, and these are the elements denoted here, and the value of x under f is f of x, f of x. So this one is f of x. So for a function, every element of the first criteria is that every element of domain has to map. For example, if I choose 1 2 3 here in set A and say 5 6 7 8, then first of all every element of 1 has to be mapped. Every element of 1 has to be mapped. If we have this example, say 3 7 and 9, and in set B I have say 2 3 and 4, 2 3 and 4. Suppose 3 is mapped to 2, 7 is mapped to 3, and 9 is not mapped, then this will not be a function. This will, first of all, every element of domain has to be mapped, and the images of the element of the set A has to be unique in set B, has to be unique in set B. So these are two basic requirement for the definition of function, that every element of domain has to be mapped. In general, say this one is not a function, and again suppose this one is set A, this one is set B, then 2 4 8 1 2 say 6 7. Just for the sake of explanation I am taking these examples. So suppose 2 is mapped to 1 as well as 2, 4 is mapped to 6 and 8 is mapped to 7. So again this type of mapping, that an element should not have more than one image in this set B. So this is again not a function, not a function. Now next example, if I take so once it's a function, we will call the set A as domain and set B as codomain. This one as domain. In layman we can call it as input and codomain as output, in fact range as output. codomain. Now let us try to understand the difference between codomain and range. Suppose in domain I have elements as say 1, 2 and 3, and let me take f of x equal to x square, Here we have 1, 4, 9, 16 and 25. So under this x square, 1 is mapped to 1, 2 is mapped to 4, 3 is mapped to 9. So clearly this one is a function. Why? Because every element of the set A is mapped and the image is unique here. But this one is not, this one is function, and the collection, the image of 1 is going to 1, 2 is going to 4, 3 is going to 9, or in other words we can say that x is mapped to f of x. So if I put x equal to 1 here, then 1 is mapped to its values is denoted by fx, or 1 say here, in this case 2 place of 2 is mapped to 4. So value of fx is 4 here, f is operating on this x, we have 4 here. So this is the notation here. The value of the domain, see in the domain we have element as 1, 2 and 3, it is taking values as 1, 4 and 9. So collection of all those values, we will call it as a range. So in some cases you may find that the image of elements of domain may be the whole set B or subset of B. This map is not onto. Why? Because 16 has no premise. See, in this case, if 2 is mapped to 4, then we call 4 as image of 2, and 2 as pre-image of 4. This is the notation which we used to we will use in general. 16 has no preimage, so this map is not onto. 25. So if there is any element in set B which has no preimage, then we will say that this function is not onto. Here in this case, say if we take 1, 2 and 3, say 4, 5 and 6. 1 is mapped to 4, 2 is mapped to 5, 3 is mapped to 6. So first of all, we need to check whether this is function or not. I have taken some finite values in both set A and B just for the sake of explanation. Similarly, we can do it for uncountable sets, infinite sets. So 1 goes to 4, 2 goes to 5, 3 goes to 6. So every element of domain is mapped here, and the images is unique here in set B, and this map is 1, 1. Whenever see two elements are different here, they have different images. So this is the definition of 1, 1. This map is again 1, 1. This map is also 1, 1. This map is 1, 1 but not onto 1, 1, because whenever one is any two elements of age say x1 is not equal to x2, then this implies their images has to be distinct if it is 1, 1. So this is definition of 1, 1. So this example is clearly of 1, 1. This one is both 1, 1 as well as onto. So I can write it as bijective map. This map is bijective, because to study this the concept of finite and infinite set, countable and uncountable set, we will do it using the concept of functions. So we need to understand that what is the definition of domain. Once a function, say in general in layman term we can call the input values this 1, 2, 3 here is the input, and the values it is taking output is 1, 4 and 9 in this one. So mathematically once it's a function, we will call this input as domain, and the values taken their collection as range. So range here is subset of codomain. It may be equal to codomain depending on the cases. So in case of bijective map is also denoted as 1, 1 and onto map. 1, 1 and onto map. 1, 1, the term for 1, 1 is also used as injective, and for onto surjective, this one. So yes. So suppose A and B be two sets, and let F be a mapping of A into B. If E is subset of A, then F of E is defined to be the set of all elements of Fx for x belonging to E. So in case if E is subset of, here we have A, B, and E is subset of A, then the images of all those elements present here, that will be this set, collection of all those images of the elements in this set E, that is called as the range set of E. This is f of E is the image of E under F. So, this is the notation used here. So, obviously, this f of E, or in fact f of A, all these images are going to be within B. So, f of A will be either equal to B, this sign here in this book is for this one, it may be equal to, f of A may be equal to B, or f of may be a proper subset of B. If f of A equal to B, we say that f maps A onto B, because in for onto map, every element of codomain must have pre-image. So, in that case, the image of A, if it is onto, then image of A will be whole set B. Now, there is another notation, set theoretic inverse. Basically, this is the set theoretic inverse. Now, in this case, we are taking E to be subset of B. Earlier here we have in case of direct image, this notation E is taken as E may be equal to A, or E may be proper subset of, or E may be empty, but we are here doing the non-trivial case. So, let us understand the concept of set theoretic inverse, and let me emphasize on this one, that for existence of set theoretic inverse, we do not require function to be 1 1 and onto. So, do not confuse it with the inverse of a function. This is just a notation used here as f inverse A. So, let me explain it with the help of example. See, if A is a mapping, suppose A and B, this one f is given here, f is given here. So, and E is any subset of B, here E we are choosing subset of B. So, how to define the set theoretic inverse of E? Basically, set theoretic inverse is collection from collection of all the elements from the domain such that f of x belongs to the set E. This is the definition of set theoretic inverse. Set theoretic inverse. Set theoretic inverse. So, better to use the term set theoretic inverse, and see within this definition we do not require function to be 1 1 onto. Here it is not mentioned that function, this one is just a notation, it has nothing to do with the 1 1ness and onto-ness of the function. Look here, it is written, if E is subset of B, then f inverse E denote the set of all x belonging to A. F inverse of E is collection of all those x belonging to the A, where image lies in this set for which we are talking the existence of set theoretic inverse. So, f of x belongs to E, f of x belongs to E. So, this one is the notation for f inverse E, that is the inverse image of a set under F. And again here we have the definition of 1 1 map and all that, which I have already discussed. Now, let us come to the point that if there exists a 1 1 mapping of A onto B, 1 1 correspondence means existence of a bijective map. So, as per definition, if there exists a 1 1 mapping of A onto B means bijective map, we say that A and B can be put in 1 1 correspondence, or that A and B have the same cardinal number, or briefly that A and B are equivalent, and in that case we write A is equivalent to B or A is similar to B if there exists at least one bijective map between A and B. So, this relation clearly has the following properties, that any set is related to any set is equivalent to in some books you will find the word similar set. So, if A is similar to B, this means there exists at least one bijective map, at least one bijective map from A to B. So, clearly every set is similar to itself. How to do this? I am giving the hint. Look at the concept of identity function. Identity function from set A to A. This one is bijective. So, with the help of identity function one can do this. Similarly, it is symmetric, that means if A is similar to B, A is equivalent to B, then we have to show that B is equivalent to A. So, how to do this? If A is equivalent to B means there exists at least one bijective map from A to B. Use the concept of set theoretic inverse. So, since there exists at least one map from A to B which is bijective, so using the set theoretic inverse concept one can show that B will be similar to A. Similarly, for transitive, that given if A is equivalent to B and B is equivalent to C, this means there exists at least one bijective map here between A and B and same from B to C. So, use the composition mapping. So, this is the hint I am giving, one can try this one. So, if it is similar, so we have covered. So, remember that this relation, the relation of similar or equivalent, this one is an equivalence relation, Now, since we have already recalled the concept of 1 and onto mapping, bijective mapping. So, the first one, what we mean by finite set. So, as per the book of Walter Rudin, here we are first of all try to understand the notations. Gn means the set 1, 2, 3 up to exactly n. This is the, so Gn is subset of natural number. Gn is subset of natural number, the counting set 1, 2, 3 and so on. This one is the counting set. If I say J3 means it will start from 1, 2 and end on 3. J4 similarly means 1, 2, 3 and 4, So, for any positive integer n, let Jn be the set whose elements are the integer 1, 2 and n. Let J be the set consisting of all positive integers. J here in this notation we are using for set of natural number. Then for any set A, when we say that a set is finite, if it is similar to Gn. Similar to Gn means there exists at least one bijective map. At least one bijective map between A and Gn. And as per this book, we will assume empty set to be finite. Empty set is assumed to be finite. For example, if I want to show that the set in which these elements are there, it is finite. So, I need to produce to show that there exists at least one Jn. Say if I choose J3 here, say 1, 2, 3, then we need to develop a 1, 1 onto relation between these two sets A and J3. So, since let me map A to 1, B to 2 and C to 3. So, clearly this map is 1, 1 and onto. So, we will say that the set A consisting of the elements A, B, C is finite. So, do not use the this one that a set is said to be finite if its element if it consists of finite elements. We are here going to define finite. So, we have to do it using the concept of function. We will always talk in terms of mapping. So, A is finite if there exists at least one bijective map between A and Gn, and empty set phi is assumed to be finite. So, this is the exact definition of finite as per the book of Walter Rudin. So, this means in case of finite set, what type of sets are going to be finite? Empty set as well as all those sets which is similar to Gn, all those sets which are similar to Gn. So, all these set we will call it as finite set. Next is infinite set. In A, so we will do in this one that all those set, infinite set means that it has to be non-empty, it should not be similar to Gn. If any set is there which is non-empty and it is not similar to, not equivalent to Jn, means there should be no mapping, bijective mapping between A and Jn. So, all those sets are termed to be infinite. So, this is a very brief, very exact proper explanation of this, the concept of finite and infinite set. Always explain it in the terms of, with the help of the concept of function. Now, the remaining one, I will give some of example. For example, infinite set, all these sets, see some of the example, we will do the proof later on. Here just I want to emphasize what we mean by infinite set using the definition of function concept. So, infinite set, for example, say all these intervals 0 1, see open interval 0 1, non trivial intervals, I mean except singleton and empty set, set of natural number, all these are infinite set, infinite set 1 by n where n belongs to n, all these sets are infinite set. Now, within infinite set, it may be countable, it may be uncountable. So, before coming to this one, to understand the concept of what we mean by countable set, what we mean by uncountable set, and what we mean by at most countable. So, it is very well given in this book. So, when we say that A is countable, if it is similar to set of natural number, a set is said to be countable if it is similar to set of natural number. So, and an uncountable set if it is neither finite nor countable. Countable set means there exists at least one bijective map between set of natural number and the given set. Uncountable if A is neither finite nor countable, and at most countable if A is finite or countable. So, A is countable here, countable set. So, any subset is said to be countable if it is similar to set of natural number, or the notation used here as J, that is A is said to be countable. In some books you will find the term countably infinite, this one is countable if there exists a bijective map between A and set of natural number, or one can use the notation J. So, I will come to this one. In some books you will find, let us first complete this one, and then I will tell some different notation used by some authors. So, A is countable if it is similar to the set of natural number. An uncountable set if it is neither finite nor countable, means A has not to be equal to phi, A is not similar to Jn. Let me write definition of uncountable set here. If I am saying that the set is uncountable set means all those set which is other than empty set, all those set which are other than empty set, all those set which are not similar to Jn, and all those set which are not similar to set of natural number. Those sets are said to be uncountable, n, or one can use the notation J here. So, this is the definition of uncountable set, that if A is neither finite nor countable, neither finite, these two are included in finite, and this is definition for countable set, that if A is similar to n, then we will say it is countable. So, it is neither finite nor countable, means A is not equal to phi, A is not equal to Jn, and A has not to be equal to n. So, the remaining type of sets will be said to be an uncountable set, and later on I will prove that its example are, say, any non-trivial interval, I mean except singleton and the empty set, and all those sets which are not similar to the set of natural number. So 0 1 all set of real number, we will prove that all any type of non-trivial interval R, all these are uncountable set of irrationals, all these are uncountable set, whereas countable sets are those sets which is similar to set of natural number. Now the remaining one is at most countable, at most countable. So at most countable means if A is finite or countable, at most countable. So within at most countable we have all those sets, say which is finite. So recall the definition of finite. Finite means either it is empty set or it is similar to Gn. So A can be equal to phi, these two are all those sets which are similar to Gn and the empty set, these two are finite. So whenever at most countable word is given, A is so all those finite set will come within at most countable set or countable. Countable means all those sets which are similar to set of natural number, say J. Notation used here is J. So this one is the definition using the concept of function to understand that to understand these terminologies of finite, infinite set, countable, uncountable set and at most countable. In some books you will find the notation that countable set is also referred for finite empty set. It may be finite, it may be empty set, it may be similar to set of natural number, but we are going to follow the standard notation here. Now countable sets are sometimes called enumerable or denumerable set. Enumeration, we can do listing with the set of natural number. Two finite sets A and B, we evidently have A is similar to B if and only if A and B contain the same number of elements. So this one is a very good approach to show that two finite sets are equivalent. So try to establish a 1 1 onto map, at least one bijective map between them. So both sets will have same number of elements. But this concept is very vague in case of infinite set. However, the idea of having the same number of elements become quite vague, whereas the notion means idea, the notion of 1 1 correspondence retains its clarity. Means notion of 1 1 correspondence, that is bijective map, to compare see in case of infinite set there are several examples where B may be proper subset of A, but still there exists a bijective map between both set B and A, whereas this case is not possible with a proper subset. In case of finite set, we cannot establish a bijective map between a proper subset of B of A. Let me explain it with the help of example. And in fact, the cardinality term will be later on you will say that this cardinality term will be only used for finite set. In case of infinite set, cardinality, that is number of distinct element in a given set, we will replace it with the concept of transfinite number. So this one is a very good example here. This notation J, actually this is the standard notation for set of natural number. In this book of Walter Rudin, it is replaced by J, and this one is for set of integers. So actually we are interested here. Look here, n is subset of Z. Clearly n is subset of Z. In fact, proper subset of Z. So I will use this notation for proper subset, because every element in n is present here. 1 is present here, 2 is present here. So n is proper subset of Z, and there exists at least one element, say -1, which is not here. So both are infinite set, but I will show that there exists at least one bijective map between these two, and both will have the same number of cardinality, and its cardinality is denoted by alif naught. So cardinality of set of natural number is alif naught, as well as set of integers is alif naught, despite n is proper subset of Z. So for this, what we will do to show that n is similar to Z, we will try to establish at least one bijective map. We need to show that there exists at least one bijective map between n and Z. There exists at least one. bijective map between n and set of natural number and set of integers. So that can be explained here using, see this mapping, we need to show that n is similar to z. To show that n is similar to set of integers, one can choose this mapping, one of the very well known mapping, f of n is equal to minus 1 to the power n box of n by 2, box of n by 2. Now look at the mapping here. For the sake of explanation, let me draw this n and z. Now if in set of natural number the first element is 1, so put f n equal to 1 here, we will get minus 1 to the power 1 minus 1 to the power 1 into box of 1 by 2. This one is the greatest integer function here. So box of 1 by 2 is 0, so overall we will get 0. So what is going on? 1 is mapped to 0, 1 is mapped to 0. Here we have 1, 2, 3, 4 and so on. In set of natural number we have 0, 1, 2, 3 and minus 1, minus 2, minus 3 and so on. Now look at the image of 2 under this mapping. So f of 2 is minus 1 square into box of 2 by 2, that is 1. So it is going to be 1. So I can also write in mapping term in short notation that 2 goes to 1, 2 goes to 1. So 2 goes to 1 here. Now similarly 3, f of 3 minus 1 cube into box of 3 by 2, that is box of 1.5 is 1 and here we have odd power, so it will give minus 1. So I can say that 3 is mapped to minus 1, 3 is mapped to minus 1. So in this way we can check that 4 is going to 2, 5 is going to minus 2 and so on. So all the now look at this one is a clearly a function because all the elements of domain is mapped in Z, and this is 1 1 as well as onto map. Whenever two elements are not equal, they have distinct images here. So this tells about that this function is 1 1. Onto also 0 is mapped to 1, the pre-image of 0 is 1, the pre-image of minus 1 is 3, pre-image of 1 is 2. So in this way it is covering positive as well as negative integers, positive numbers as well as negative numbers including 0. So clearly this map is 1 1 and onto, 1 1 and onto. So this so since there by definition we have at least one map which between n and z which is both 1 1 and onto, so clearly n is similar to z. So this means cardinality of both the set, cardinality of the set of natural numbers is equal to cardinality of set of integers. Since cardinality of set of natural number is already assigned as assumed as alif naught, so cardinality of set of integers is also alif naught because we have established a 1 1 onto map despite n is proper subset of z, despite n is proper subset of z. So actually all this contribution goes to the mathematician Cantor, who according to who established all these results, that within an infinite set we can compare that which one is bigger, which one is smaller. Now next another example, just for the sake of understanding, for there is another one based on geometry. Look, if someone asks that whether we have on 0 1, say this one whole as R, whole real line say minus infinity to infinity, and this one is 0 1. Which has more number of real numbers? I mean the number of points lying on 0 1 or the whole R. Clearly 0 1, closed interval 0 1 or say open interval 0 1 is subset of R, in fact proper subset of R, but we will see that still both have same cardinality, and that later on we will prove that its cardinality is basically 2 raised to the power alif naught continuum. So I am trying to give you a geometrical idea, that is we need to establish at least one map between, if these two sets are similar, if 0 1 is similar to R, then I need to produce at least one, always use the concept of function to show that there exists at least one map from 0 1 to R. So, how to show that? Just a geometric idea. Its center is say half, draw a semicircle here, draw a semicircle here. Now, whatever y I will choose here, whatever y I will choose here, join this y with its center. Now, the points where it cut the circumference, this one, take projection here. So, for this y we have x here. Now, choose a different element here, again choose a different element here, join it with the center, it is going to cut here. For this different element I have this different element. So, whenever two elements are different here, we have their different images, and every element of the codomain has pre-image. So, in this way one can establish a 1 1 and onto map, 1 1 and onto map, to show that these two are equivalent, equivalent, or the term used here similar, 0 1 is similar to R. Now, another advantage of understanding this, the concept of countable and uncountable set, we will use it in this union concept. Say AI is the family of sets. Now, this notation I is equal to 1 to n, or the notation I is equal to 1 to infinity AI, I can use only this notation if I know that the collection of this these sets, collection of all these sets is countable, at most countable, at most countable. So, whenever it is countable, then I can exhaust it with the set of natural number or its subset, say Gn, and empty set is assumed to be countable. So, if countable means we can do listing with the set of natural number, one can exhaust it with the set of natural number. In layman terms, it stands for I can do it numbering with the set of natural number or its subset, but I cannot use this notation if, say for example, this I is coming from R. If this I is coming from, say R, or say interval 0 1, then since this set is uncountable, so I cannot write here 1 to n or in this way. This is not allowed. This is only allowed if the set is countable. If the set is countable, that is at most countable. So, there we will use the concept of index set and index set. So, in that case, we will use the concept of index set, indexed family of set. Indexed family of set. What it says that let this capital lambda be a non-empty set, be a non-empty set if for each lambda belonging to the index set we are given a set, say A lambda, then we say A lambda, where lambda belonging to the index set, capital lambda, is a family of sets indexed by the set A, indexed by the set A. So, whenever a collection of set is given, whenever a collection of set is given, say A lambda, this collection may be empty, this collection may be finite, this collection may be infinite, within infinite it may be countable, it may be uncountable. So, if an arbitrary collection is given, then we will use the concept of index set. We will use the concept of index set. We will not use this definition. If an arbitrary collection is given, arbitrary collection of set is given, then I cannot use this notation 1 to n or 1 to infinity of ai. This notation is not allowed unless it is claimed that it is given that the collection is countable or at most countable. So, in that case, if this is arbitrary collection, then we have to use the concept of index set, which we will cover later on. So, for the next topic, we need this where these are the important terminologies of finite infinite set. Now, recall here we have covered finite, the difference between finite and infinite set, countable and uncountable set, and the different notions, the different notations adopted by some authors, the concept of this countable and the difference between countable and at most countable. So, this all I have covered from the book of Walter Rudin. And once I cover this the concept of representation of real numbers, and the nested interval lemma, then I will come back to the to some proofs of uncountable set, that we will that to show that whether a given suppose some question is given that whether show that this set is uncountable. So, contrary to it, we will assume that suppose the set is countable. The technique is that we will assume that the set is countable, and since it is countable, so it can be listed with the set of natural number or its subset, say Jn, and then using the method of contradiction we will do the proof. So, that point as I discussed, that we will cover it after understanding the concept of the representation of real numbers, its interpretation in ternary, binary, decimal form, and we will also do some of the proof using the concept of nested interval lemma.